This is a Softrock Ensemble RXTX, an SDR transceiver. I'm going to investigate it and try to correct any errors that I find, and then start to adapt Linrad to use this. I'm running it on a modern computer with an X9DAI board from Supermicro. It doesn't have any PCI slots, but I have a StarTech PCIe to PCI adapter and also a Delta 44 sound card. As it turns out, Delta 44 requires Windows XP 32-bit. Any other Windows version doesn't provide correctly working drive routines for this sound card. I have connected this signal generator to the input of the Softrock Ensemble, and what I see on the screen is like this. So I click on the signal here, and as you can see, I have adjusted the S meter to show minus 50 dBm, which is then in agreement with the signal generator setting. The bandwidth is 10 kilohertz, and I click on the noise floor a little bit to the side here. Well, I have to have it outside the filter, and then the level is here. You can read it out. Minus 103 dBm, and in a single hertz that would be minus 143. So 143 minus 174 is something like 30 decibels. It's a very high noise figure. Something is not quite right here. I'm using this switch power supply to give 12 volts to the Softrock. I have a non-switching regulated power supply, so I will change from the switch power to the passive regulator. Look at the screen here. This is what we have, and look at the S meter. And I disconnect the power. Then things go wrong. And connect the passive, and you can see it's much better. We are now at minus 113. That is minus 153. That corresponds to a noise figure of 21 decibels, which is normal for a receiver for HF. Now I'm connecting a capacitor from the antenna ground to the ground of the audio, like this. And look at the screen. Here you have spurs at 14.144 or something. And with the capacitor in place, they are gone. What is more remarkable is when I go to the switch power supply, and here we are back at the noisy switch power supply, and I put the capacitor between RF and audio ground. like that. You can see that the noise floor goes down to a good value, and also the spurs disappear. There should be a capacitor from antenna to audio ground, one that doesn't allow overtones of 50 Hz, but which would short circuit HF, that is megahertz and above. What we need is a capacitor from here to here. Maybe 0.1 microfarad or 0.03 microfarad or something like that. When I short circuit the sound card like this, the level comes out at -119, and with 10 kHz bandwidth that is 159. And that would correspond to a noise figure of 15 decibels. The noise from the Softrock will add to this and degrade the noise floor to some extent, but not very much. I have added 47 nanofarads from antenna ground to audio ground. The signal is of course still as -50 decibels. And if I look about 10 kHz away, about here, the noise floor, as you can see, -113. That is with the passive regulator. I switch the power supply now to the other one. The switch power supply. And we had 113.65 minus 115. That's half a decibel. So it is a major improvement by that capacitor. Now, if the capacitor were made too large, I can simulate that by short-circuiting from analog ground to RF ground like this. Then look at the center. The audio problems that are within up to about 5 kHz. I remove that short circuit, and you see the difference. So the capacitor must not be too big, but big enough to get rid of the RF interference from power supplies. Now, selecting a frequency where there is no spur, I see the noise floor here as 115.68. That is 116.7 minus 174 equals, that was wrong, 155.7, because we have 10 kilohertz bandwidth, minus 174 equals 18.3 decibels. That's the noise figure of the setup with a passive regulator and with a capacitor that I just added. That is, I think, a reasonable performance for an RF radio. This is the point of saturation. I have now connected a very pure crystal oscillator, and I step up the signal level by 2 decibels. And you can see there are many harmonics in the audio, creating a large number of false responses. Just adding a single decibel is not permitted. If I go 1 decibel below this maximum level, like that, you can see that the differences are small. So this is approximately the maximum level tolerated by the Softrock. And it is minus 18 dBm. The noise floor about 10 kilohertz away, it's about here, is at minus 114.5. That's a dynamic range of 136.7 in a bandwidth of 1 Hertz. And if I switch off the strong signal, like this, you can see that the noise floor does not go down more than 1 dB or so. Well, we can read it out. 115.49. It didn't change much. So reciprocal mixing is not a problem in the Softrock. I'm now running under Windows 7, the 32-bit version. The drive routine is not quite okay. There are glitches occasionally, as you can see. Best seen in the waterfall. Here we had some. The level is now 6 decibels below the point of saturation for the sound card, but it is at the point of saturation for the Softrock. This drive routine allows me to increase the level. I can click here, minus 10 dB, and as it happens, the level is 0.8 decibels below the saturation of the Delta 44, and this is fine. I have now connected the signal generator at minus 50 dBm, and as you can see, the S meter no longer shows minus 50. The signal is about 5.5 dB stronger, because I turned up the gain on the Delta 44, having that possibility. I have now changed the S-meter calibration, and the S-meter again shows minus 50 dBm, which is the level of the signal I'm tuned to. The noise floor is now minus 116.1 in 10 kilohertz bandwidth. That is 17.9 dB noise figure. 40 decibels for the 10 kilohertz, and room temperature is minus 174 dBm. The small improvement in the noise figure is because of a big improvement in the Delta 44. Now, when I have set it to saturate at the same point as where the Softrock saturates. So the noise floor, when the input to the Delta 44 is shorted, is now as minus 122.2. That is something like 5 dB lower than before, if I remember correctly. Would correspond to a noise figure of about 11 decibels. So the noise from the Softrock degrades the Delta 44 by, well, I already forgotten the numbers, but you can find it out. With the strong signal present, we have those glitches that belong to some problem in the sound driver. Here we can see that the noise floor, when things go right, is at minus 115. If I disconnect the strong signal, like that, the noise floor drops by maybe 1.5 dB. So we can clearly see a little bit more of the reciprocal mixing, but it's still a small phenomenon. Even with a strong signal there, the dominating contribution to the noise is the noise of the Softrock, thermal noise or whatever it is, and not reciprocal mixing. The local oscillator is quite good. So here we have the noise floor at minus 115, and I click on the signal and find that the signal level is minus 17.7. .97 dB in 10 kilohertz is very good. To make it easier to visualize what it means, I have set the bandwidth to 500 Hertz, which is the standard bandwidth that people tend to use in measurements of amateur radio. And I tuned to the strong signal and changed the S-meter calibration to make it show 0 dB on the carrier. And then I click 2 kilohertz away. It means I move 2 kilohertz and click here. Now I'm tuned 2 kilohertz from the strong signal, and I can see the level is 110 decibels lower. So the dynamic range is 110 dB. Compare that to this information. The best radio at 2 kilohertz is at 101. And I scroll down to the next page, and you can see not everything is as good as those relatively modern receivers. This document is by Rob Sherwood, and this is the first page of it. Here I'm running Rocky with the same hardware and the same signal. And as you can hear, the problems of the Delta 44 driver are less important, but if I move the mouse a little bit like this, you can see there are these problems again. If I switch off the strong signal like this, you can see, as in Linrod, the noise floor does not change much. I put it back. So the Softrock receive side is very good. I have now set the signal generator to 0 dBm and connected it to a Perseus through some attenuators. And I get this spectrum, and I have set the S-meter calibration to make it show 0 dBm. So it means at the input of the attenuator, this system now is calibrated correctly in power. Rocky is now in transmit mode. I can set the level of the carrier here, and I have straight key and key down at this moment. On the Perseus, I see this. There are some glitches, but between them we have the transmit spectrum. I will increase the level in the Rocky. It's now minus 12.2, minus 10.8, minus 9.4. We start to see many more spurs starting to come up. And the level is not quite 30 dBm yet. Minus 6.6 here according to Rocky, and this is obviously too much. And this setting goes in fairly large steps. If I go down, minus 8, this is still too much. Minus 9.4, I would say a little bit too much. The power now is 28.8. That's nearly a little bit more than 1 dB below the nominal 1 watt power. So I reduce a little bit more, minus 10.8, and we had 28.7 here, 28.9, okay, and now it is 28.8. We are in compression mode, so and that is very obvious if you look at the noise floor. I place the mouse on the noise floor and then reduce the level a little bit more, minus 13.5, and you can see very clearly that the noise floor is now higher. Some spurs are significantly lower, here from red to green, and here and here. There are spurs coming up at a lower level, this one for example. So I decide that I will run this unit at minus 13.5, sort of reasonable maximum power. And then the output is 27.8 dBm. That is a little bit more than half a watt. Now I set the bandwidth to 500 Hertz. Like that. And then change the S-meter calibration. First 0. And then I read what is the level we have. 12.3. And now the carrier shows 0 on a relative dB scale. And I click on the noise floor here. And what we see is that the noise floor is 100 decibels down. It looks very ugly when you see the spectrum here, but actually it is not so bad. It is 100 decibels, or 101 perhaps. It should be 110. That's what they have, I think, close to the carrier. Let's say here. we have a little bit better than 110. There is high frequency noise on the audio that reaches the mixer. If I release the key, like that, you can see that the noise goes up because we are still in compression. I look at the peak level here, and you can see that when the key is up, the noise floor is 96 decibels below full carrier power. So this unit can be improved significantly. I don't know exactly how to do it. I will have a look and see if I can come up with something. I have closed Rocky while it was in transmit mode, and we have this noise spectrum, and the S meter is here at 96 or so below full carrier power. I can disconnect the cable from the Delta 44 on the transmit side, this one, and that solves the problem. So it's not the Softrock, it is the sound card. So I put back the Delta 44 and go to the control window and change the sampling rate. Now it's 24 kilohertz, 16 kilohertz, 12, 11, 9, 8 kilohertz. It's very obvious that the sound card is doing something. There are settings for the output. It doesn't matter what I do with them. So I restore 96 kilohertz again. Look here. This is the output of the Delta 44. And here. And that's when I connect it through the breakout box. This is an audio attenuator. Resistors of 270 ohm and 820 ohms. It's a little bit more than 10 decibels attenuation. And this makes a big difference. Here the signal is at 0 on the S meter scale, and the worst noise floor here is now minus 113 or maybe 112 and a half. And close range, if I click on the signal, where is it? Here, here, and go 2 kilohertz away. So I go in the baseband and click 2 kilohertz away. 1, 2 here. I get tuned to this frequency, and we can see the dynamic range is 110 decibels. So that's the same as on the receive side. And then if I go another, let's say, what could it be, 2 more kilohertz, like that, it drops a little down to the same level that we have on the noise maximum. Some maybe 20 kilohertz away, the noise floor is even lower. You can see what it looks like here. Now, just adding an attenuator that allows me to bring up the signal by 10 dB, or a little bit more than that, 12 and a half. That reduces the noise by 12.5 dB because the noise is independent on the signal level. So bringing it up and then attenuating with resistors makes this improvement. What should be done is, of course, to add a filter that cuts above 48 kHz or maybe cuts above 5 kHz, depending on how the transmitter will be used. Two possibilities. One is to place the signal very close to the center, always, and move the local oscillator to where transmissions are wanted. And the other is to keep the local oscillator fixed and move the audio tone up and down as desired. Anyway, performance is sufficiently good. This is not a problem. This kind of architecture does have problem in principle. That's because the D to A converters don't have a 16-bit DA. They have a smaller number of bits, but they run at much higher frequencies. And then noise is added at some fairly high frequency to interpolate between the levels of the actual D to A converter. Sigma delta conversion, I think it's called. This is an article I wrote for Dubus a couple of years ago. It was motivated by an observation of the noise emitted by Flex 1500. There is this table with performance data, and you can see the flex radius are around 80 decibels. Compare that to 114 that we found in the Softrock. That's a more than 30 decibels difference. Conventional radios are in the range 100 to 110 dB, with one exception, that's the K3, which is significantly better. This article describes this problem with the digital to analog converters, and you can see something very similar to what we have seen now on the Softrock, but here the phenomenon is far too strong. In the Softrock with the attenuator it is perfectly okay. This is what I see on the spectrum analyzer from 0 to 20 MHz. And the power level is 27.7 dBm according to this instrument. And this is what I see from 0 up to 100 MHz. The overtones are not very strong. Not a problem, I think. This is what I see from 0 to 1 GHz. This could be maybe a problem. Emitting signals on 600 MHz at a level of minus 24 dBm. Maybe that's not so good. I don't know what services are and how these frequencies change when frequencies of the SI 570 are changed. But a very simple filter would eliminate this. The performance we can see around 115 dB at something like 5 or 10 kilohertz. That's a property of the Delta 44, not of the Softrock. The Softrock is better than this, I think. Anyway, if you use the Softrock with some other sound card, there is a risk that this other sound card is similar to the sound cards used in the Flex 1500, and then performance would be awful, and it would be absolutely necessary to add a low-pass filter to eliminate the DA converter noise. I have never investigated several different sound cards for this. It's something that would be interesting to do in the future. But before that, I'm going to rewrite Linrad to add the control functions needed to use the Softrock with the Delta 44 under Windows XP, where I have proper drive routines for the Delta 44.